Ringwoodite is a high-pressure phase of magnesium silicate formed at high temperatures and pressures of the Earth's mantle between 525 and 660 kilometers, 326 and 410 miles depth. It is polymorphous with the olivine phase forsterite, a magnesium iron silicate. Ringwoodite is notable for being able to contain hydroxide ions, oxygen and hydrogen atoms bound together within its structure, combined with evidence of its occurrence deep in the Earth's mantle. This suggests that there is from 1 to 3 times the world ocean's equivalent of water in the mantle transition zone from 410 to 660 kilometers deep. This mineral was first identified in the Tenham meteorite in 1969. And it is inferred to be present in large quantity in the Earth's mantle. Ringwoodite was named after the Australian earth scientist Ted Ringwood, 1930 to 1993, who studied polymorphic phase transitions in the common mantle minerals olivine and pyroxene at pressures equivalent to depths as great as about 600 kilometers. Olivine, wadsleyite, and ringwoodite are polymorphs found in the upper mantle of the Earth, at depths greater than about 660 kilometers. Other minerals, including some with the perovskite structure, are stable. The properties of these minerals determine many of the properties of the mantle. Characteristics: ringwoodite is polymorphous with forsterite, Mg, 2 silicon oxide, and has a spinel structure. Spinel group minerals crystallize in the isometric system with an octahedral habit. Olivine is most abundant in the upper mantle, above about 410 kilometers, 250 miles. The olivine polymorphs wadsleyite and ringwoodite are thought to dominate the transition zone of the mantle, a zone present from about 410 to 660 kilometers depth. Ringwoodite is thought to be the most abundant mineral phase in the lower part of Earth's transition zone. The physical and chemical property of this mineral partly determine properties of the mantle at those depths. The pressure range for stability of ringwoodite lies in the approximate range from 18 to 23 gigapascals. Apart from the mantle, natural ringwoodite has been found in many shocked chondritic meteorites, in which the ringwoodite occurs as fine-grained polycrystalline aggregates. Natural ringwoodite generally contains much more Mg than Fe but can form a gapless solid solution series from the pure Mg end member to the pure Fe end member. The latter has been discovered in a natural sample only recently and was named Occurrences, in honor of U.S. mineral physicist Thomas J. Occurrences, 1936 to 2010. Geological occurrences. In meteorites, ringwoodite occurs in the veinlets of quenched shock melt, cutting the matrix and replacing olivine, probably produced during shock metamorphism. In Earth's interior, olivine occurs in the upper mantle at depths less than about 410 kilometers. And ringwoodite is inferred to be present within the transition zone from about 520 to 660 kilometers depth. Seismic activity discontinuities at about 410 kilometers, 520 kilometers, and at 660 kilometers depth have been attributed to phase changes involving olivine and its polymorphs. The 520 km depth discontinuity is generally believed to be caused by the transition of the olivine polymorph wadsleyite beta phase to ringwoodite gamma phase, while the 660 km depth discontinuity by the phase transformation of ringwoodite gamma phase to a silicate perovskite plus magnesio-wustite. Ringwoodite in the lower half of the transition zone is inferred to play a pivotal role in mantle dynamics, and the plastic properties of ringwoodite are thought to be critical in determining flow of material in this part of the mantle. The solubility of hydroxide in ringwoodite is important because of the effect of hydrogen upon rheology. Ringwoodite, synthesized at conditions appropriate for the transition zone, has been found to contain up to 2.6% water. Because the transition zone between the Earth's upper and lower mantle helps govern the scale of mass and heat transport throughout the Earth, the presence of water within this region, whether global or localized, may have a significant effect on mantle rheology and therefore mantle circulation. In regions of subduction zones, the Ringwoodite stability field hosts high levels of seismicity. An ultra-deep diamond found in Huina, Mato Grosso in western Brazil, contained inclusions of Ringwoodite, the only known sample of natural terrestrial origin, thus providing evidence of significant amounts of water as hydroxide in the Earth's mantle. The gemstone, about 5 mm long, was blasted up from the depths by a diatreme eruption. The Ringwoodite inclusion is too small to see with the eye. The mantle reservoir is found to contain about 3 times more water, in the form of hydroxide contained within the Wadsleyite and Ringwoodite crystal structure, than the Earth's oceans combined. Crystal structure. Ringwoodite crystallizes in the isometric crystal system with space group Fd 3 meters. On an atomic scale, magnesium and silicon are in octahedral and tetrahedral coordination with oxygen, respectively. The CO and MgO bonds are both ionic and covalent. The cubic unit cell parameter is 8.063 A for pure magnesium silicate and 8.234 A for pure iron 2 silicate. Chemical composition. Ringwoodite compositions range from pure magnesium silicate to iron 2 silicate in synthesis experiments. Ringwoodite can incorporate up to 2.6% by weight H2O. Physical properties. The physical properties of ringwoodite are affected by pressure and temperature. The calculated density value of ringwoodite is 3.564 grams per cc for pure magnesium silicate, 3.691 for Fo90 composition of typical mantle, and 4.845 for iron 2 silicate. It is an isotropic mineral with an index of refraction N equals 1.768. The color of ringwoodite varies between the meteorites, between different ringwoodite-bearing aggregates, and even in one single aggregate. The ringwoodite aggregates can show every shade of blue, purple, gray and green, or they have no color at all. A closer look at colored aggregates shows that the color is not homogeneous, but seems to originate from something with a size similar to the ringwoodite crystallites. In synthetic samples, pure Mg ringwoodite is colorless, whereas samples containing more than 1 mol% iron 2 silicate are deep blue in color. The color is thought to be due to Fe2+, Fe3+ charge transfer.